All right. Hello, everyone. So I'm gonna run through some announcements, some logistics things. So the major thing is your all's test is in 1 week. That's the most important thing that you all need to know right now is that your test is a week from today in this room. It is going to be just like the last test in terms of the structure, in terms of how it all goes. It'll be 20 multiple choice questions. There will be 2 true responses where you'll pick one. The multiple choice will be worth 80% of the test. True response will be worth 20% of the test. The formula sheet, I will give you a formula sheet. The formula sheet is posted on the files tab. So it is the same one as the last test. There's a very slight modification to it. So last test, when I gave you all the formula sheet, I hadn't updated it. I used to do harmonic motion, and I swapped that out for center of mass. So it should look basically, you probably look at this and it won't look any different to you, but very subtly, there's center of mass stuff and universal gravitational potential energy. And I got rid of a couple other equations that were on here that you can use. So anyway, that's the equation sheet you're going to get verbatim. That is copy and pasted into the test. So you'll know exactly what formulas you have access to. Like before, you can bring a 5x8 note card with whatever you want written on it. I will bring those note cards to hand out on Thursday. I don't have them right now. So I'll bring it on Thursday. Thursday's a review day. Just like last time, we'll go through the concepts, we'll practice problems. It'll be a good time. Review day is always generally pretty useful. Show up or don't. Up to you. There will be no attendance or clicker questions. I'll record it. I'll post all the things. But I've made 3 resources for you all that may or may not be useful to you, but they exist. And I sent out an announcement with them with details of them. So I'm just going to talk you through those. One is test 2 review, which is what I'm going to talk through very briefly at the beginning of class. It is an overview of all the major concepts. And I'm actually going to open it on here because I want to show you all a couple of things with it. This can be relevant. So, All right. So, just like test 1, every slide is a summary of 1 week's worth of content. So the 4 weeks of content are working kinetic energy, conservation of energy, momentum, and then universal gravity / center of mass. Now, this looks really messy, and you're like, man, that looks really messy. I sure wish I could get rid of all that handwriting. At any point when you all download my PowerPoints, if you just go to review, you can click the hide ink button, and it just hides it. It does not delete it. So then if you want to see it, you just click the button and it magically shows up again. Quite handy. So this is a nice little kind of summary. And then there's a bunch of random things. So on Thursday, I'll start with a blank slide. But this is what I wrote last year. And so maybe or maybe not, it's meaningful to you. But I figure might as well include it because if you do think it's nonsense, which it kind of looks like nonsense, you can just hide it. So it's there if you want it. If you can make sense of it, great. If not, on Thursday, I'm going to make it. So yeah, we'll talk through each of these, and then there's some example problems at the end that I worked through last year. Again, I'll work through those / other ones, except this one. If I double the length of the pendulum, it has effective period. Do not worry about that one. Obviously, I haven't taught. If you're like, I haven't heard the word pendulum in this class before, that's because I haven't used it. Oh, this one's not updated. All right, that's why. This is not the one I actually posted. The one I posted has a slide for center of mass. Let me show you all that one, just so you don't think I'm a liar. It's in a different folder. So there's a whole slide. I updated it. Last year I taught harmonic oscillators, so that's why you saw that. This year is center of mass. Ta-da. And I actually deleted the harmonic. There's no pendulum. I deleted that one. So anyway, that's there. That's one resource. A summary of all the topics that were covered, just so you know what's going to be on the test. Great. What's another thing I made for you all? So again, in this folder is everything. I made all the clicker questions. I just copy and pasted them into one PowerPoint. So there's a PowerPoint with every single clicker question I've asked. It's 49 of them, it turns out, including one couple that we're going to cover today. All the answers, all the work I did is on here. Same thing when you're looking through these. If you're like, man, I don't want to see the answer, just go to review, click hide ink, and ta-da, it's all gone and you can't see the answers. And you're like, I want to check the answer. Then you click the button and it all appears and ooh, magic. But yeah, these are the clicker questions. These are good practice. It is important to practice the conceptual questions. So at least like skim through these. And then the last thing I made for you all is one of the things that was mentioned was going through the problem set. So the problem set is actually broken down by topics. So you can actually really easily determine if I'm in work and kinetic energy, I'm probably going to use work and kinetic energy to solve these problems. If I'm in momentum, I'm probably going to use momentum to solve these problems. On the test, I do not give you sections. I don't say this is a momentum problem or this is an energy problem or whatever. And so to help you all kind of study for that, all I did was I took the problem sets. So there's this thing called problem set 2 solutions mixed, where all I did was I just moved the problems around. I did what the title says. I mixed them up. It does not tell you what type of problem it is. It just says problem set 2 mixed, and then it's all the problems in one giant list. So the purpose of this is you can kind of just go through this and because a skill is, can you look at a problem and say it's this type of problem? Can you look at a problem and say it's an energy problem? Can you look at a problem and say it's a momentum problem? Can you look at a problem and say it's a center of mass problem? So on and so forth. So this is another way of kind of looking at things so that you can practice in the way that the test is going to look. And then if you're like, man, but how do I test if I'm right? So for example, this one, an average size asteroid is moving towards Earth with a certain velocity. What will be its speed before it hits the atmosphere? What is its kinetic energy? So, look at this. See if y'all can figure out what type of problem this is. Give y'all a few seconds. What type of problem is this? I got an asteroid headed towards the Earth. And I know how far away it starts, I know its mass, I know its velocity, and I want to find its velocity right before it hits the atmosphere. You do need to know the radius of the Earth. So I would give you that in the test. So then you say, man, I think it's a blank type of problem. I think it's an energy type of problem. Maybe. So you just control C. You jump over to the one where it is organized. You control F. And where'd it go? We couldn't find what you're looking for. Oh, that's why. I copied the question number. It is not question number 10 anymore. There it is. All right, what's this one in? Oh, it's a universal gravity problem. So it is conservation of energy. In this one, you do have to use universal gravity in that as well. So again, it's just another way to kind of prepare. It's another resource. Use it or don't. Up to you. But it was something that people had mentioned was they wanted the problems mixed together, so I mixed them together. Easy peasy. Okay. Otherwise, for studying for the test, same old strats, y'all. Solve the problem sets, look through the quizzes. Look through the quicker questions. So, straightforward. All right. Any questions about the test that's upcoming? All right. It will be the normal class time, hour, 20 minutes, all that jazz. Reminder to you all, if you're using SAS accommodations, please submit those sooner than later. I do want you all to make use of any resources, anything you have. Those things, accommodations exist for a reason. Please make use of them. I always want to encourage people to do so. There we go. All right, so today we're going to finish up. Last class we finished up universal gravity. So just to give you the highlights there. Universal gravity, there's a force, there's an equation for it. If you want to make it acceleration, just divide by mass, and that's going to show up. Which slide is that one on? Ooh, it's somewhere in here. If you want the acceleration, just divide by mass, and that's going to get rid of the mass, and there it is. Fantastic. Remember that things go in a circular motion. So you can set the gravitational force equal to the centripetal force. Very exciting, very useful. And that I mean sincerely, not sarcastically. And then you have the universal gravity. universal gravitational potential energy, and we use that to find escape velocity and do things, and it was cool. It let you figure out how fast you need to do to get away from the Earth. And that's where I ended. Now we're going to move on to center of mass. And before I introduce any equations with it, I'm going to give you some kind of intro of why is it useful. Also, you know more than you realize concerning this. That's kind of the beginning of this presentation is basically you know more than you might realize about this topic. So, if I had the following triangular shaped roof, approximately, where would I place a single vertical beam to support it? Would I put it at point A, which is over here, point B, which is kind of off to the left, point C a little bit middle to the right, or point D all the way to the right? This is something you've been experiencing and seeing your entire life. Oh, I thought the problem was in. All right, so I'll make the other slides from the things I want to talk about. Oh, I got to open the question. Don't overthink it. This is not a trick question. It's to show you all that you know things about center of mass, even if I haven't taught you any math related to it. That is the purpose of this. All right, we'll go for 10 more seconds. In 5, 4, 3, 2, 1. Again, this one, if you don't believe me, this is one where I'm just going to say this is the answer, and then you can kind of test it for yourself. Pretty much most people got it right. It's at point B. Point B is the magic spot. Test this for yourself. Find some triangle block somewhere or something. And you will find that point B roughly, approximately, is where you want to place it. Again, I haven't taught you any math related to this. This is just based on your experiences in life. Balancing things as a kid, you probably tried to balance things on your fingers, or even as a, whatever. That's a normal thing people do. So I'm going to teach you all why that is. And it turns out, in physics, we like to simplify things. You're going to end up enjoying, it's super useful in engineering as well. And it turns out this object with its semi-complex geometry, we can take all that mass and figure out where the center of it is. And we're going to figure out how to do that. And the center of mass is going to end up being right here. You got more mass on the left, so that kind of weights there. But this mass over here is farther away, and that's going to matter. But if you average it all out, it's going to average that you can pretty much pretend as if this object is a single point located above this pillar. And I'm going to give you a few more examples to kind of make sense of this before we get to the math. So that's one example. Here's another one. This is going to be weird because I'm going to play a YouTube video while streaming a YouTube video. So I don't know what that does for things. All right, so this is a really cool demo that I wish I could actually show in class. So one of my TAs actually found this in my other class. And it's really cool because it kind of shows why this is useful. We don't have this thing here, otherwise I would do it. So I'm just going to kind of skip through it. So this is a tennis racket that's getting tossed, and it looks like a really complex motion. When you look at, and there's another object, it looks complex. You got this thing spinning, and it's all sorts of crazy. There's another object that looks complex. Okay. Now, what they have done on this object is they have found the center of mass, and they put like a sticker on it that shines under UV light. So when you have a UV light, black light, it really shines on this dot. It's the same exact object, but the center of mass is marked. And what's cool is they toss it the exact same, but it's going to look way different. It's the same exact object, but it doesn't look all crazy this time. So if y'all notice, this is the tennis racket. It's going to go in order. And it looks like a nice parabolic path. And then they're going to do the other crazy object. Nice parabolic path. And then, I guess the same one. So what this is showcasing is that if you know where the center of mass is, you don't care about how the thing is kind of spread out as far as like projectile motion is concerned. As far as projectile motion is concerned, you don't care. Now, this one, you get a little bit of wiggle because they didn't have center of mass. When they do center of mass, you don't get the wiggle anymore. So anyhow, it's a very, very useful tool. We have been doing it the entire time in this class without realizing it. When I told you all I tossed Dimmo Duck across the room, you didn't care that Dimmo Duck was in the shape of a duck. You didn't care whether Dimmo Duck was spinning. You didn't care how the mass was distributed. You basically pretend that Dimmo Duck was a single dot flying through the air. And that's how you did your math. We are going to find where that dot is located. That's basically what we're going to be doing with this. So that's one example to kind of convey to you why center of mass is useful, why I'm covering it. The other, and I'm going to give you all two examples of this. What do you have, if I lean forward, if you stand up and lean forward, what do you have to do to prevent yourself from falling? So this is not going to be a clicker question because, my goodness, I don't know how I'm going to come up with the answers for this. Like multiple choice answers. Think about it. Normally, I'd say stand up and do it, and you could. Feel free. There's not much room in these hallways. If you stand up and you lean forward, you will fall. Like, that's going to happen. If I lean forward, I will naturally fall, but there's something I can do to prevent myself from falling. What do you do naturally every single day of your life to keep yourself from... Anyway, think about it. Talk about it. All right, and this is one of those, the more you think about it, you probably don't even think about what you're doing. You do this naturally. You do this naturally. Like, you all bend down to pick up things all the time. But when you think about it, it's kind of hard to maybe remember. So the game that's happening here, when I lean forward, so when I'm standing up, here's me. Life as well. I'm not going to fall. When I lean forward, what happens? My center of mass, so your center of mass is somewhere like the middle of your torso, belly button, I don't know, somewhere around there. When you lean forward, your center of mass shifts forward. Here's the problem. Your feet aren't under your center of mass. So we're going to learn about torque eventually. Gravity is affecting the center of mass, and it's pulling it down, and we're going to learn about torque, and that results in you falling. So what do? Well, if your center of mass is in front of your feet or behind your feet, you will fall. That is a guarantee. Your feet are not attached to the floor. You don't have any like screws bolting you down to the floor. So if your center of mass is forward, gravity pulls you forward and you fall. So what do? And you do this naturally without thinking about it. You can stick your foot out. What is sticking my foot out? Look, I'm leaning forward and I stick my foot out. What am I doing? By sticking my foot out, I am shifting the center of mass back to the center above my foot. That is what you are doing when you are balancing. You are shifting the center of mass above your feet. If your center of mass is ever in front of your feet or behind your feet, you will fall. And also related to this, spreading my legs apart does nothing for me because it doesn't affect the center of mass in the X direction. XY independence. Spreading your legs doesn't help you from falling forwards or backwards. So again, center of mass comes up there. This also, again, a really subtle one that you may not even realize. Even when you lean forward like this, and you're leaning forward, you're not falling. That's because I'm sticking my butt backwards. You do this naturally without realizing it. Your body is trained itself that when you lean forward, you stick your butt backwards so that the center of mass stays above your feet. So, center of mass all over the place. Very, very important for determining how something's going to behave, whether or not it's going to rotate and things like that. There is one more example I'm going to give you all. And I'll just mention it, balancing tires. So whenever y'all get tires on your car, they have to do something called balancing it. And balancing your tire, when you buy a tire, the center mass for a tire is not guaranteed to be dead center. It's not guaranteed to be dead center. So let's say your center is this red dot. It could be shifted. And if your center of mass is not balanced on your tire, your wheel will wobble. And it will put strain on the axle in your car. So when you buy tires, they do something called balancing. You can just they have these fancy equipment. I say fancy, it's just something that spins a tire. Balancing a tire. They have these things that spin a tire really quickly. And then it detects the force and things like that. And it tells the technician where to put masses. So how do you fix this? They put a mass over here on this side to shift the center mass back to the center. So there's little lead weights that are attached to your tire. If you look carefully, you'll find them somewhere. And they're literally doing that to shift the center of mass back to the center. So center of mass is all over the place when it comes to mechanical systems. Very, very, very important concept. So we're going to talk about how to calculate it. That's the motivation. That's the reason we're spending time on it. So now the question is, how do you calculate center of mass? So I'm going to walk through the derivation. I'm going to show you all the equation. And then I'm going to give you an example that has nothing to do with center of mass, but it's the same exact math, and it's going to be for calculating your GPA. The math for calculating your GPA in college is the exact same math for calculating center of mass. So, anywho, all right, center of mass derivation. F equals ma. Hopefully we're cool with that. And then this equals the change in momentum over change in time. That's a definition we introduced, but if you're like, where did that come from? Remember that A equals dv dt? So if you have mdv is dp. If you're like, what the heck's going on there? Great. F equals dp dt. There's that. The sum of the forces, so ma equals the sum of dp dt, just coming from that equation. If you have multiple objects, you got to account for that. So capital M here means more than one. Pull out the derivative. So again, we got that original. Just pull out the dt. So you get d dt, sum of p. Well, what is p? P is m times v. V is dr dt. Great. What's the whole point? What the heck? Why are we doing all this? So what we're going to do, so I'm going to erase this. So where is this coming from? Because this step might look a little weird. Remember, y'all, that ma equals the sum of all forces. Sum of all forces equals ma. So I just sum up all the dp's, dt's. Okay? So, hey, here's P. Here's P. And so we're going to take, if P is that, and we're going to take this whole thing, and that's P. So we're just going to stick it right there. We're going to stick what P is. It's m dr dt. So all we did was take that and put it right here. Okay? dr dt, I'm just going to pull out the time derivative. So I'm just going to pull out this time derivative and chuck it here. So that gives me a second time derivative. And then I'm going to move the mass to the other side. Divide both sides by mass. Divide both sides by mass. Mass cancels. And I get this thing. Acceleration equals the second time derivative of 1 over m, sum of mr squared. This is all I care about. This is all I care about. This is center of mass. This is how we're going to find center of mass. Center of mass. So after all this derivation, all this stuff I did, you don't need to know the derivation, but I always want to show you all, any equation I give you isn't made up. It's a bunch of logical steps using concepts you all do understand. You all do know that F equals ma. You all do know that acceleration is dv dt. So like all these steps are things you know. We're just stringing them together. And from this comes the equation for center of mass, which is 1 over capital M. That's the sum of all the masses. Sum all the masses together. times a summation of each individual mass times how far away it is from the origin. So 1 over the total mass times, take each mass, multiply it by how far away it is, and then add all those terms together. And this is the equation for it, and this looks, I don't know how y'all feel about this, but even like, when I look at this, I'm like, that doesn't look very pleasant. There's a bunch of letters there, and it looks overwhelming. You got this J. J just represents objects. If I have 5 objects, I just M1, then M2, then M3, then M4, then M5. J is an index. If you are doing coding, that's the term that's getting indexed. It's a weighted average. Center of mass is a weighted average. When we have the mass of each object, and it gets weighted by how far away it is. The farther away it is, the more it impacts the center of mass. Okay? Center of mass is a weighted average. Your GPA is a weighted average. So the next clicker question is going to be, hey, here's some fake credit hour classes with some random GPAs associated with them. Find the GPA. And if you can do that, you can do center of mass. It's the exact same thing. So we'll see how that goes. If you can't, that's fine. I'm going to teach you how to do center of mass. But if you can, then I've made this equation look way less gross for a lot of you. That's the goal. And then we'll practice it and hopefully make sense of it for everyone. X and Y are independent of each other. There is a center of mass in the X coordinate system. There's a center of mass in the Y coordinate system. The X and Y are separate. Remember, y'all, if you don't want to fall over, spreading my legs does not help me from falling forwards or backwards. It does absolutely nothing. I could try to do a split, and I'm still going to fall over if I lean forward. Moving my legs apart does not affect the center of mass forwards and backwards. If I want to do that, I've got to move my legs forwards and backwards. So, X and Y are independent. Don't forget that. They're vectors. All right. So, and we'll see if you can do, I have no idea. I don't know if you all have ever calculated your GPA before or anything like that. We're going to find out. What would be your GPA given the following courses? There are 3 classes: physics, history, underwater basket weaving. This student got a 4.0 in physics, they got a 3.0 in history, and they got a 2.0 in underwater basket weaving. However, these each have different credits associated with them. Some have more credits and therefore carry more weight. So the credits, and I guess I should phrase it. Unfortunately, it kind of works a little differently. The credits here is kind of like our mass. So to give you all the analogy ahead of time, our credits are like our mass, and our GPA is like how far away you are to measure kind of how far you get in it. So, see if you all can figure out the GPA of this. What would be your average GPA given these performance in the courses and given how many credits each class is worth? It's a weighted average. And that's what we consider mass. That's the calculation. That's the idea. And while you're deliberating on this, the joke of the day is the local bakery went out of business. They ran out of dough. All right, we'll go for like 15 more seconds. And 5, 4, 3, 2, 1. All right, so let's think this through. We are trying to find basically the average GPA, the weighted average. But here's the problem. I can't just add 4 plus 3 plus 2 and divide by 3. I can't just do that because these are different credit hours. A class that has more credit hours carries more weight. If you get a low score in a class that has a lot of credit hours, it will affect your GPA more negatively versus one that's 1 credit hour. So how do we account for that? We take each one, so 4, and we multiply it by how much it's weighted by that mass. So we do 4 times 4 plus 3 times 3 plus 2 times 5. Now, if you just plug that in your calculator and say, that's my GPA, you're going to get a ridiculously large number that doesn't make any sense. So we weighted each of these, but now we need to divide out that weight. We need to standardize this. How do we standardize it? We divide by the sum of the things we weighted it by the total credit hours. Because I kind of want the GPA per credit hour is kind of, I guess, the idea. And if you do all this math, so 16 plus 9, that's 25. So you get 35 over 12. And if you do that math, you get this, 2.92, which y'all did great on. Look, if I gave you this exact same problem, this problem is a center of mass problem. Let me just change it for y'all so you can see how this would be a center of mass problem. So, what would be the center of mass? Given the distances and masses. So, object 1, object 2, and object 3. Instead of this is where it's located. Location, or let's say distance from origin. That's going to be a really key phrase. You have to define the origin. You have to define where they're measured with respect to. And then their mass. And ta-da, the answer is exactly the same. Where is the center of mass? If I have 3 objects, object 1 has a mass of 4 kilograms and is 4 meters away. Object 2 is a mass of 3 kilograms and is 3 meters away. Object 3 is 2 meters away and has a mass of 5 kilograms. It's the same problem. So this is what I wanted to convey to you all. That equation that I showed you all before, our center of mass equals 1 over, add up all the masses, and multiply that by how far away each mass is times its mass. That is literally what you just did. These two things are the same. Okay? So now we're going to practice it. Yeah?
Like when you're solving for center of mass, you have to variable for the answer.
Yeah, that's a good question. So in this case, the variable would be meters. Yeah, so center of mass is a location. It's where is the center of mass located with respect to the origin. And so your unit for center of mass will always be a distance. which is a great question. Yep, it does have a unit. It's where you're located. All right, so we are going to build towards it. We're going to start with the first example, which is 2 objects in 1 dimension. The next problem after that, we're going to do 3 objects in 2 dimensions. And then after that, we're going to do an object with a continuous mass distribution where I give you the density, and we'll get to there. All right, so we start with the simplest case. Fine. I mean, it looks complicated just because it's big numbers, but this is a simple case. Once we draw a picture, you'll see that. Find the center of mass for the Earth-Moon system using Earth's center as the origin. You have to define an origin. Remember the first question I asked you all this class is where is Dibble Duck located? And the answer was, every answer is right, unless you define an origin. So, Earth center is the origin. The mass of the Earth is 5.97 times 10 to the 24 kilograms. The mass of the Moon is 7.36 times 10 to the 22 kilograms. And the distance from the center of the Earth to the center of the Moon, I'll clarify that here, but that's kind of assumed. From the center of the Earth to the center of the Moon is 3.85 times 10 to the 8 meters. And then I gave you the radius of the Earth, and I'm just going to tell you we don't need that. I've kind of changed this problem in a couple ways. How far away is the center of mass from Earth's surface? And there's the answers, and don't worry about them. In fact, I'm going to copy and paste this and not put the answers because sometimes people get too distracted by that. All right, they will come back. So we draw a picture. There's Earth. There's the Moon. 2 objects. We can, because these are nice spherical objects, you know what? I could draw them as spheres, but you know what's even easier? 2 dots. They are 2 dots as far as I'm concerned. I don't really care that they're spheres. I'm going to approximate them as single dots. In this picture, I know the mass of this dot is 5.97 times 10 to the 24 kilograms. I know the mass of this dot, which is the Moon. You know, I'll put mass Earth and mass Moon. Equals 7.36 times 10 to the 22 kilograms. And then the last thing is I know this distance. I know that they are 3.85 times 10 to the 8 meters apart. All right, so there's my pretty picture. I got 2 dots. We can just condense them into dots. You've been doing that this entire class without realizing it. You've been doing it in every single problem. When you drew a picture, you really didn't care what the shape of that object was. It never mattered. You just were pretending they were dots without realizing it. So moving forward now, we can actually recognize that. So we got mass of Earth, and I don't want to rewrite all that because... So we got the mass of the Earth. I'm going to put that up there. Yeah, I'll just rewrite it. Write our givens. 5.97 e to the 24 kilograms. Mass of the Moon is 7.36 times 10 to the 22. And I'm actually going to not put a couple variables for a second because I want to make a point. So in this problem, it says the Earth is the origin. The Earth is the origin. This is 0, 0. Everything is measured with, in this problem, distances are measured with respect to where the center of the Earth is. Very, very important. You're going to see very quickly why. Again, I'm going to come back to step 1. I'm going to fill in a couple more givens. But to give you some context, I'm going to go to the next couple steps first. We are solving for the center of mass of these 2 objects, of this 2-object system. Where is the center of mass located? In the case of the system, the interesting part of this is they both orbit the center of mass. When you have a 2-body system, they orbit, actually any object system, 10 objects, and there's orbits involved, they orbit the center of mass. The Moon does not orbit the center of the Earth. And the Earth actually does orbit a spot, and we're going to find out where it is. They both are orbiting this. If you have a binary star system, they orbit a center mass that's somewhere in between them. If the masses are more similar, you can check that out. It's interesting. So, the center of mass equation is 1 over the sum of the masses times where the masses are located times their individual masses. That's the center of mass equation. And I'm going to write this out a bit. Equals 1 over the sum of the masses, very straightforward. You just sum the masses. Very straightforward. This second one, we're going to find the mass of the Earth times the distance that the Earth is away. RE here is not the radius of the Earth. RE is not the radius of the Earth. This is the distance of the Earth from the origin. It's a very subtle thing that if you mess this up, you get the wrong answer. Distance of Earth from origin. That's why we have to define the origin. Where is this thing located? R is a measure of where is it located. With respect to what? The origin. Always the origin. Okay? Plus the mass of the moon times where the moon is located with respect to the origin. And then I'm going to pause and I'm going to help. I want you all to finish step 1. Figure out the value of RE. Figure out the value of RM based on the picture. I'll give you all a few moments to do that. All right, give you all a few more seconds. Last chance to make your guesses before I spoil it for you. All right, so how far away is the Earth? How far is the center of the mass of the Earth from the origin? 0. Where is the Earth located with respect to the origin? It's literally sitting right on top of it. The Earth is 0 meters away from the origin. It's literally defined as the origin. How far away am I from myself? 0 meters. How far away are you from yourself? 0 meters. What is very important is whatever you define the origin is, everything is measured with respect to it. You cannot move the origin around. Once you set it, it needs to stay there for every single measurement. Otherwise, you get wrong results. All right, where is the moon located? The moon is located 3.85 times 10 to the 8 meters away from the origin. Again, this R here is not radius. A really common notation thing we'll do, little r is location, position. Little r is position, capital R is radius. That's a really common notation we'll use to help keep them separated. So these are little r's, it's position, not radius. Okay. So we're going to set up this math. So we're just going to copy all this over and just plug in numbers. I'm going to delete the problem. Leave the answer up there. So yeah, center of mass. We're just going to find it by plugging stuff into here. So step 4, center of mass. Our center of mass equals 1 over the mass of the Earth, which is 5.97 times 10 to the 24. 5.97 times 10 to the 24 plus the mass of the moon, which is 7.36 times 10 to the 22. And we're going to multiply that times 0, because the first term goes to 0, times the mass of the moon, which is 7.36 times 10 to the 22, times how far away the moon is, its position. So a really natural question here is you might be really uncomfortable with that 0 and be like, doesn't the Earth affect it? Doesn't the mass of the Earth matter? Yeah, remember y'all, the mass of the Earth is still here. That's where that weighted at, like the mass of the Earth, we're dividing by that. It is affecting the number. We didn't just get rid of the Earth entirely. Like the Earth still matters. It shows up in this denominator term. That's what's going to shift the center of mass kind of to the left, where we expect it to be. So you plug all that in, and you should get 4.64 times 10 to the 6 meters. And so what's really interesting about this, the radius of the Earth is about 6 times 10 to the 6. The center of mass of the Earth and moon is about 2/3 the radius of the Earth. The Earth is actually orbiting a spot 2/3 away from its inside. Now, this picture was not to scale. Like the moon is actually like way out here. This is nowhere to scale. Like even that's probably not to scale. So if you're like, man, that's a significant thing. I haven't drawn this to scale. The moon is like way off in the distance kind of thing. So just keep that in mind. But yeah, it's an interesting thing. The Earth is actually orbiting because of the moon, they're orbiting a shared location. Yeah.
How would it affect if the origin was instead of the moon?
That's a good question. If instead we set the moon as the origin, you get the exact same result. But instead of measuring that value from here to here, you would get this value. Yeah, so the position, the final result you get is where you're located with respect to the origin. So our answer here says that our center mass is 4.64 times 10 to 6 meters away from the origin, which is probably the center. Yeah. Whereas if you did it for the moon, your answer would be whatever number from the center of the moon. Yeah, which is a great point. So you get the same result, it's just a different perspective. Yeah.
Would getting a negative center of mass tell you which way it goes?
Yes, that's a great question. Yeah. When getting a negative center of mass, what does that tell you? It tells you you're to the left of the origin. I could have said the center of mass was located in the middle of the entire system, at which point I would have gotten a center of mass off to the left, a negative value. Yep. If I tell you I'm 5 meters away, that tells you nothing until I tell you where the origin is. And now you have perspective. So, really, really important thing that we can sometimes forget about. Coordinate systems, defining it is important. All right, so we got a couple problems. Let's do great, one-dimensional problem. Dunzo. You know what's more fun than a one-dimensional problem? A two-dimensional problem. 3 point masses are placed at the corner of a triangle as shown in the figure below. Find the center mass of this 3-mass system. And I tell you where the origin is. If I give you a center mass problem, I have to tell you where the origin is, or every answer is correct. I have to tell you where the origin is, or any answers, well, you'd have to tell me where your origin is. So in this case, where is the origin? In the bottom right. That object is the origin. Everything is measured with respect to the origin. And this is where I'm actually going to make a table, because I think a table, just like we did the GPAs, we made a table. Making a table for this will actually just help us organize the information. I can make a giant list of all the masses, and then all their x coordinates, and then all their y coordinates. If I make a nice table, it's just a bit better. I'm going to call these Object 1, Object 2, and Object 3. Just makes my life easier. I'm going to call the Object 1, 200 kilogram, the Object 2, 75 kilogram, Object 3, the 150 gram. I say kilogram. What's really cool, nice about center mass, you don't have to convert units. If you look at the center of mass equation, the masses cancel. The units will cancel for masses, and your answer will just spit out the units you put in. I will convert them just for consistency's sake.
The origin is where it has the biggest mass, and the previous problem, Earth has the bigger mass, and it's the origin.
Yep.
Are all center of mass problems going to be like that?
That's a good question. So in this case, the origin is where the largest object is. That was more coincidental. In general, you will pick the origin to be where one of the objects is because it makes your math easier. Because that term will just get multiplied by 0, so it's one less thing to plug in a calculator. But no, I could have made the origin at the 100 gram or the 75 gram, and it would all be fine. That's a great question, though. Where you choose the origin is completely up to you. Okay, in the problems, I'm going to tell you where it is. But in general, if this is outside this class, you can pick any spot you want. So we're just going to make a nice little table because it makes my life easier to write this down. It's nice and organized. So we're going to make a table with their masses. We're going to make a table of their x coordinates, and we're going to make a table of their y coordinates. Remember, y'all, x and y are separate. You have to split things into x and y. You're going to find a center of mass in the x. You're going to find a center of mass in the y, and they are completely independent of each other. So mass 1 is going to be 100. And I will just convert these to kilograms, but I'm telling you all, center mass is one of those special equations where you don't have to actually worry about unit conversions. And you can kind of investigate why that is yourself. It's a fun little exercise. But to not confuse anyone, I will convert. Writing small is difficult. All right, and 0.15 kilograms. Great, I put the masses in there because that's really obvious, fairly straightforward. I want you all to find the x and y coordinates. And if you want, you can leave them in centimeters, but I will put them in meters just to keep things simple. Yeah.
On the test, if we don't convert like grams to kilo or centimeters to like inches or meters, will that matter?
So if it's a free response, I won't care. If it's a multiple choice, you just want your answer to match my answers. Yep. Good question. So yeah, always match whatever the units my answers are. I mean, you'll have to pick the one that's right. All right, so for the sake of time, let's just go through. So object 1, and this is where one of your students actually made mention of this previously. If you put and I need to make this, I need more space. If you put the x coordinate as 0.04, and that's all you put for the x coordinate, you are missing something. The answer for the x coordinate is 0.04. Make this pen a little bit smaller. But it's negative. If you do not put the negative, you will get the wrong answer. These are vectors. If you're located to the left of the origin, you need to acknowledge that. Mathematically, it does not work. Otherwise, you're just assuming everything is on the right, and this problem is not stated that way, so you get the wrong answer. All right, my y coordinate for object 1 is 0. That's real nice. Object 2, the x coordinate is 0. The y coordinate is 0.03. Positive because it's above. And this problem that looks worse is actually look at all these zeros. It's very, very nice. So step 2, what are we solving for? We are solving for the center of mass. And the beauty of vectors is you have so much fun doing physics, you get to do it twice. So you're going to find the x center mass, which is the sum of masses times the mass times its x coordinate. You're going to find the y center mass, which is 1 over the sum of the masses times the masses times their y coordinates. This I here is not initial. This I is an index. However many objects. I have 3 objects here, so I'm going to sum it 3 times. If I had 7 objects, I'd sum 7 objects. And then I'm just going to copy and paste this all to a new slide. And we're getting a little tight on time, so I'm just going to quickly solve this through because I do need to show you all how to do the last case, which is a continuous mass. I want to make certain I at least cover it. We'll have some time on Thursday if I need to finish anything, but okay, so step 4 is really straightforward. X center mass is going to be 1 over, add those numbers up, 0.1 plus 0.075 plus 0.15, and you're going to multiply that times negative 0.4 times 0. The first term is 0. Nope, it's not. My bad. 0.1 times its x coordinate plus 0 plus 0. The x coordinate of object 2 is 0. 0 times its mass is 0. The x coordinate of object 3 is 0. 0 times its mass is 0. So you solve that, and that spits out a number, which is going to be negative 0.0123. And because I did all my things in the answers in meters. Do the exact same thing for the y, but just use y's. Sum up the masses. Object 1, its y coordinate is 0. Object 2, its y coordinate is not 0, so we actually have to plug it in. And object 3, its y coordinate is 0. And you plug that in, and we get 0.0069 meters. So if we draw where the center of mass is, these are locations. My x coordinate is 1.23 centimeters to the left. So it's going to be about here. That's my x coordinate. My y coordinate is just shy of 1 centimeter. So that's here. So long story short, my center of mass is right there. It's a little bit to the left and it's a little bit up based on these coordinates that we found. And this is an interesting thing. The center of mass of an object does not have to be on that object. Remember when we leaned over, the center of mass could be in the air. That's how boomerangs work. Boomerangs, the center of mass is in between the arms of it. The center of mass does not need to be on the object itself. Okay. So in the last 20 minutes, I need to show you all for a continuous object, and then that'll be it. And we'll be done. So we've done center mass for a bunch of discrete individual objects. So the follow-up to this is, what if I have an object? So let's go to the original example I gave you all. I'm going to skip the next clicker question because I don't have time for it. What if I have an object whose mass varies based on location? So I gave you all that triangle in the beginning. And I'm going to tell you all this triangle can be approximated as an object whose mass varies based on the location. If we're really close to the left, we get a lot of mass. If we're really far to the right, we get a little bit of mass. So my mass varies based on where you're located. And so I'm just going to show you all that if you have an object, so this is my OG equation. This thing that looks really gross in the beginning is the one we've been working with. This is just the center of mass equation that we've been working with. Great. But if I have an object that's continuous, I got to sum up all the infinite things. If you want to think about it like I'm summing up every single atom. Every single atom, I'm finding where it's located in its mass. And how small is an atom? dm. dm is just a really small mass. So I'm adding up an infinite number of objects and where they're located. What is a sum of an infinite number of objects? It's an integral. An integral is an infinite sum. That's all an integral is. It's an infinite sum of infinitely small things. Whenever you integrate, you're just adding in a cool way. That's what's cool about calculus. It lets you add infinite small things. So ta-da! We just turned this equation. 1 over m is just the integral of dm. Literally add up all the infinitely small masses and you get the mass. So this integral here is m. It's the total mass. If you integrate dm, you get m. Then this integral over here is just where am I located, r, times my infinitely small object. And you integrate that. Now here's the problem. Where I'm located, my mass may be different. R is not a constant. So we're not actually integrating. We're integrating all the masses together, but we need to integrate over the length of the object. So we need to change this dm into like a dr. Somehow, some way. That's basically the trick here. How can we actually integrate this? I need to integrate over r. I need to integrate over the length of my object so I can add up all the masses. How do I do that? If only we had a function that kind of expressed how mass was, spread out in an object. If only there was a nice expression for how the mass is spread out in an object. I kind of spoiled it there. What is it? What's the expression? What's the magic word that tells you how mass is spread out? Yeah, density. Now remember chemistry? What the heck is the equation for density, mass, and volume? We're going to need this. Remember your chemistry. Is it mass divided by volume, mass times volume, volume divided by mass, or mass divided by volume squared? Ten seconds. And 5, 4, 3, 2, 1. All right, so this is one of those you know it or you don't, or you Googled it real quick. It's mass over volume. It's how much mass per unit volume. Now, we could do this, and we could do a three-dimensional integral over volume. Volume is 3 dimensions, which means we need to do a triple integral. And technically, you're spared because you may or may not have taken Calc 3. It's no requirement. So, instead of over a volume, we're going to instead look at a line. We're just going to simplify that. So it turns out density is mass over volume. It turns out there's one for this is called a surface density. It's mass over area. And then there's going to be one, and this is on the next slide. This is called rho. It is a linear mass density. We're just going to work in one dimension because we haven't learned double integrals or triple integrals yet, so I'm sparing you the suffering. So rho, it's like a P without the top part. Rho is mass over length because it's one dimension instead of volume, it's length. Rearrange that. So mass equals rho times L. You just multiply it over, and then you take the derivative of both sides, and ta-da, you get dm equals rho dl. And then you just chuck that where the dm is, and instead of L, we're going to say x. We're going to integrate from the x coordinate. L is just where you're located, how far you're located. So we're just going to replace L with x, and ta-da! This is the equation for calculating center of mass for something with a non-uniform density, which do exist. So this dm goes right here as well. So you get 1 over rho dx. This is literally just the total mass. And then this, which is just r dm. But we can actually integrate it now. And that is what we'll do for our last problem. I'm going to give you a density function. So I'm going to give you a function that says the density of an object based on location. and then we'll just integrate it, and we'll get an answer, and it'll be lovely. Lots of fun. And you may be like, why would I do this? Reminder to you all that a triangle is basically an object where its density, you can approximate this triangle as something with a lot of mass, and then its mass gets less and less and less. So it's actually a way of approximating complex objects. An object with a geometry like this, I could approximate as an object with its density changing as a function of length. Just cool. A lot of the clever solutions are taking something and making it look like something you can actually solve. As weird as that sounds. That's the people that are clever. They take problems that look impossible and they change them into problems that you can actually solve using skills and tools that you have at your disposal. All right, so this is just a slide that's nice and organized that says the same thing. If you have an object whose density changes with respect to location, this is a function for it. Where x is where you're located, x is position with respect to the origin, that's still true. All right, and let's just do a problem with it. That's the last thing we're doing today. Find the center mass for a thin bar of length 20 centimeters whose density is distributed according to the function rho of x equals square root of x plus 2x squared, where x equals 0 to the left end, i.e. the origin is at the left end. And assume that rho is measured in gram per centimeter and x is in centimeter just so that you can solve my problems. Make your life a little easier. So I got a bar. Where this is my origin. It's just a 1D problem, so that's the 0 side. And then this side is 20 centimeters away. 0. So this one we actually do have to work in centimeters. This function is a function of gram per centimeter, so we cannot convert our units, otherwise you'll run into problems. So we do need to stick in our centimeters, otherwise we're going to run into problems. So yeah, our givens, we have our density function, square root of x plus 2x squared. We have my initial, we have where I start. We have our bounds. We have the bounds of our integral. Step 2, solve for the center of mass. Step 3, what's the equation? It's going to be integral of rho dx times the integral of x rho dx. That's just the one that I gave you on the last slide. And step 4, do the thing. 1 over the integral you all try setting up the integral. It's all there. Try it out. We got time. Put the things in. See if you can write the integral correctly. But yeah, this is how most center masses are calculated. If you have an object with a weird shape, you got to do an integral. And you have to know how the mass is distributed, whether by its shape or by its density function, either one or both. So yeah, 1 over the integral of square root of x plus 2x squared dx, where my bounds are 0 to 20, times the integral of x times parentheses square root of x plus 2x squared dx, also evaluated from 0 to 20. And then it's just an exercise in doing the integral. Which, it's a nice integral. It's a nice simple integral. So the first integral we can evaluate, that's going to be 1 over x. Square root of x is x to the 1/2. So it's going to go up a number. But that means I need a 2/3 in front of it to cancel out that exponent when it comes back down. And then I'm going to have x to the 3rd. Same thing. Exponent goes up, but I need a 3 on the bottom to cancel it out. And then I have the integral, and this one I'll do in a couple steps. So this is x to the 3/2, x times square root of x, adding exponents, plus 2x cubed, adding exponents. And this one is evaluated from 0 to 20, but I'm just going to leave that nonsense there. 2/3 x to the 3/2 plus 2/3. Oh, and there's bounds here. 0 to 20. 2/3 x to the 3rd, evaluated from 0 to 20, times, this one's also 0 to 20, x to the 5/2, and you got your bounds. That's the wrong number. I need a 2/5 to cancel out the 5/2. That drops down. And then x to the 4th, and I got a 2, and I need a 4 to cancel the 4. That drops down. Evaluated from 0 to 20. All right, the bottom term, everything's got x, so 0 is going to get rid of all that. So really, we're just going to plug in 20. So you get 2/5. Gosh, how am I going to write this to save me the most space as possible? 1 over 2/3 times 20 to the 3/2 plus 2/3 times 20 to the 3rd times 2/5 times 20 to the 5/2 plus 2 over 4. That's just 1/2. I'm not going to. Woo! All right, you plug that in the calculator, and my answer in the problem set is not quite correct, but the answer should be 14 point, I believe it's like 97. There you go. And that's where my center of mass is located with respect to the left side of the bar. There you go, using calculus and physics. And that's, we're finishing a little bit early today, but yeah, start practicing on all the things, y'all. Energy, momentums, gravity, universal gravity, center of mass. And Thursdays are a good day. I'll be here with no cards.